All right, in objective 4.3, we're going to calculate the probabilities of compound events using a tree diagram. This is actually very related to 4.1 when we made sample spaces. 4.1 is good for situations like flipping a coin where you could get heads or tails. Heads and tails are equally likely to occur, so 1/2 and 1/2. Sample spaces are really good for situations like that. 4.3 which is tree diagrams, also could apply to that, but makes it a little more work. What 4.3 is good for are situations where the probabilities are not the same. So like if you're drawing a card out of a deck and we're talking about getting an ace or getting a not ace, these are not equally probable. So getting an ace is much less likely than getting a not ace. So a tree diagram is better for situations like that. So that's what this explains here. And this is best to just kind of see how this works. So let's see. In the state of Louisiana, 47% of voters are Democrats, 28% are Republicans, 25% are not registered by party. We call those independents. In 2016, in the presidential election, 33% of Democrats voted for Trump, 96% of Republicans, and 63% of non-affiliated voters, independents, voted for Trump. Overall, what percentage of Louisiana voters voted for Trump? So this is, you notice, multiple, it's hard to call this events, but kind of like multiple parts to what's going on here. First, it tells us the percentage of people who are registered in each way. That's the first part. Then it tells us what they did in the election. So this is kind of what I mean by two events. We've got two different things going on here, and the first one kind of, happens first. So here's how we do this. You're going to need a fair amount of space, and the first thing that happens is we know that there's three options for what they could be. They could be Democrats, so I'll put a D. They could be Republicans, R, or they could be independent, and I'll put an I. They told us the percentage of what happens here. So they said 47% of voters are registered Democrats. I'm going to put 0.47. Please don't put the number 47. This won't work out. 28% are Republicans, so 0.28. And then 25% are independents, so 0.25. This is the first branch of the tree. And if you add all this up, it adds up to 100%. That should always be the case. Then they tell us that each of these three situations could have voted for Trump or not Trump. And they gave us percentages for that too. So if you're a Democrat, you could have either voted for Trump or you could have voted for not Trump. I'll put NT. If you're a Republican, you could have voted for Trump or you could have voted for not Trump. And if you're an independent, you could have voted for Trump or you could have voted for not Trump. So the first branch of the tree diagram had three branches, and then each of those branches has two more branches based on the possible outcomes. We're now going to fill in the percentages here. So they said 33% of Democrats voted for Trump, so that's 0.33. And because we know that the branches, like the two branches of one level must add up to 100%, this then must be 0.67 because 33% and 67% add up to 100. We're not going to necessarily need all these numbers, but I just want to show you where they come from because sometimes you do. Then it says 96% of registered Republicans voted for Trump, so 0.96 voted for Trump, and 0.04 did not. And then for independents, we had 63% of them voted for Trump, 0.63, and therefore 37%, 0.37 did not. Each branch, each set of branches adds up to 100%. Now we have to go to the question. And just like in the last objective, the question that they ask is important. So they said, what percentage of voters voted for Trump? There's a total of 1, 2, 3, 4, 5, 6 branches. And of those 6 branches, 3 of them are branches that voted for Trump. Okay, so either Democrat Trump, Republican Trump, or Independent Trump. I want to say that this is really important. They didn't have to ask this. They could have asked different questions. They could have said what percentage didn't vote for Trump. They could have said what percentage of Democrats and Republicans voted for their party, so like Democrat not Trump, Republican Trump, you just always have to read the question. So in this case, it's voted for Trump, so it's these three. And now in order to do these calculations, you need to multiply all the branches that led up to that. So for this first row, it's 0.47 times 0.33, and you do need to show this work. For the second row, it's 0.28 times 0.96. And then for the third row, it's 0.25 times 0.63. Again, it's all the branches that led up to where you are. I have a calculator with me, and I recommend you do too. I'm multiplying these together, and then I'm going to round everything to 4 decimal places if it goes farther. Otherwise, that's the standard. So this is 0.115 or 1551. The next one, 0.28 times 0.96 is 0.2688. The next one, 0.25 times 0.63 is 0.1575. And what each of these means, 0.1575 means of all the people in Louisiana, 15.75% of them were independents who voted for Trump. So this gives you kind of like that breakdown of the breakdown. The last thing we're going to do here is just add all these up. This will give you the total percentage of people in Louisiana who voted for Trump. Even though this seems unnecessary, I need you guys to put pluses here and then like an equals line, like an addition line there, because they're looking that you know that you have to add those numbers. So 0.1551 plus 0.2688 plus 0.1575 comes out to 0.5814. So that means in Louisiana, 58.14% of people voted for Donald Trump in 2016. Let's go on to the next example. Two people, A and B, are playing rock, paper, scissors. We did an example like this in the last one as well. Ignoring when they tie, they're playing best 2 out of 3. And then they give us some information about how this goes down. So before we get into percentages, I want to actually just make the tree diagram. So either A could win first or B could win first. Then after A wins, they play again because it's best 2 out of 3. And either A wins again or B wins. And then if B wins first, it's kind of the same thing. Either A wins first or B wins. But then notice what happens here. If A won twice, they're done. But if A won, then B won, then they have to play a third time. So that one, it comes out again. So A could win or B could win. And then if B, A won, then same thing. Either A could win or B could win. This is not the easiest thing to notice, but the important thing about this example is I want you to see that it does not matter if all the branches don't reach the same length like they did in the last example. Sometimes it happens like this. Now let's throw in some percentages, and I'm going to read this carefully. It says person A tends to win 80% of the time on the first throw. So let's put that in. Person A wins 0.8% of the time, 80%, which means person B wins 20% of the time, 0.2. This is going to be a little weird. 40% of the time that they have won the previous throw. So if A won, then it's a 40% chance that they win again, which means it's a 60% chance that they lost. The other place on this where A had won the previous throw is right here. See how right here A won the previous throw? So there's a 40% chance that they win again and a 60% chance that they lose again. And person A wins 20% of the time they have lost the previous throw. So if B won, then it's a 20% chance for A winning the next throw, which means 80% for B. That also occurs here, 20% for A, 80% for B, given that B won the previous throw. You might want to re-watch this section if you need to. I know there was kind of a lot going on here. Now the question, they could have asked anything. They could have asked what's the probability that it goes 2 games, or the probability it goes 3 games, or the probability that A wins or B wins. In this case, they asked what's the probability that person A wins. Well, let's see, that's A would win, or A, that would be A winning, or BAA, that would be A winning. All the other situations result in B winning. So this first one is 0.8 times 0.4, which comes out to, I'm just multiplying this on my calculator, 0.8 times 0.4, 0.32. This next row is 0.8 times 0.6 times 0.2. So 0.8 times 0.6 times 0.2 is 0.096. And then this last one down here where A wins is 0.2 times 0.2 times 0.4. This seems like the least likely because all those numbers are low. So when I multiply them, I get 0.016. Sorry, 0.016. And then finally, to get the total probability that A wins, we just need to add all these together. So when we do that, 0.32 plus 0.096 plus 0.016, we get 0.432. So there's a 43.2% chance that person A wins this match. We have one more example here. And again, this one's going to be a little bit different. That's why we're doing it. A drawer has 10 white socks and 6 black socks in it, not pairs, just loose individual socks. If you choose 2 socks in a row without looking, what's the probability that you get 2 socks of the same color? So, first event, you choose a sock. It could either be white or black. Second event, you choose another sock. It could be white or black, and that occurs for both of these. So the tree part of this tree diagram is probably the easy part. The hard part is going to be the probabilities. So they said, I'm going to go to a picture that I made. They said that there's 10 white and 6 black socks. And therefore, the probability of choosing a white sock the first time is 10 out of 16, right? So we're going to go back over here, and I'm going to write this as a fraction, but you could easily write it as a decimal if you wanted as a percent. So there's 10 out of 16 probability of choosing white, and therefore 6 out of 16 probability of choosing black. Here's where this is going to get a little bit different. Once you have chosen a white sock, you have taken that sock out of the situation. The second sock, well, there's no longer 10 white socks, now there's 9. So now the second white sock is going to be 9 out of 15 instead of 10 out of 16. So I'm going to go back here and write these out. So this is going to be 9 out of 15. And if you just subtract 15 minus 9, that means there's 6 black socks left out of 15. In this second situation, it's kind of similar. This time, again, the probability of getting a white sock first is 6 out of 16. And then if a black sock is pulled first, now the probability of getting another white is, I'm sorry, I made a mistake here. The probability of getting a white was 10 out of 16. Now the probability of getting a second white is going to still be 10. There's still 10 left, but there's no longer 16. Now there's only 15 left because we took out one of the blacks. So going back to our probability, our tree diagram, the probability of getting a second white sock or a white sock after you've chosen a black is, is 10 out of 15. And then getting a black and then another black would be 5 out of 15 because there were 5 blacks left out of 15 total left. Now, the question here is, what's the probability you get 2 socks of the same color? Well, that's either white, white, or black, black. So white, white would be 10 sixteenths times 9 fifteenths. When I multiply that together, it comes out to 0.375. And then black, black would be 6 sixteenths times 5 fifteenths. So when I multiply that, I get 0.125. Again, if you don't like the way the fractions look, you could have turned these into decimals much earlier. Finally, we add these together, and we get, by coincidence, just exactly 0.5. So the probability of getting 2 socks of the same color is 50%.